So until last week, we introduced the homogeneous transformation and also the Euler system and the royal pitch system. We did not introduce the royal pitch system, but it's kind of in-class homework before I let the students can perform the matrix operation with the royal pitch system. We will find some time to let you turn out as a homework, in-class homework. But today we will go forward a little bit. It's called Forward Kinematics. We better finish that everything. I believe I can finish the inverse kinematics also, and maybe some Jacobian introduction before the next week. Yeah, because after next week I will introduce two speakers from Ch3. They can introduce the real application for robot, and I hope you can explore your vision and the application for the robotics system. Okay. For the forward kinematics is our today's point. Okay. If we want to describe the motion of a robot, and at this point we don't consider about the force at the moment, because the force and moment is belong to the dynamics. As I mentioned in the first class, kinematics and dynamics is quite different. It's quite different. Okay, but if you have interest, the book I introduced to you, they contain everything. Okay, but we don't have a too long class to introduce it all. But for the advanced topic for the robotics, actually when you perform your practical class, 实习, practical class, actually you can use as a tool, and I believe the textbook can help you a lot. Okay, so for the forward kinematics problem is we want to determine the position and the orientation for the end-effector. We only care about the end-effector. Before the end-effector, the arm, the upper arm or lower arm, we don't really care about the position at all. Yeah, because what we need to do is we, as a human being, we have two arms, but we focus on the hand part, the palms part. Okay, and the finger is kind of the ultimate design from the God, if you are religions for Christian. I would say we can use for this. We can use this kind of fingers, 5 fingers at least, and to perform a lot of tasks, almost any task. Okay, so we care about the end-effector. Although right now the robotics end-effector is not so complicated, but we can see the future from the Tesla robot or Boston Dynamic, and you can see the palm design mimic to the human being will become very popular, especially in your age. Will become very popular. So in our laboratory, we also conduct this kind of research for one group, and at the point, it's not only the end effect. We need to control the finger position. So it's quite a, I would say, brain burning stuff. But we're still going, I would say, looking for the research topic in this field. Okay. As we mentioned last week, we introduced the homogeneous transformation. It means we can contain the rotation matrix and the position matrix together, and we will adapt the kind of concept in this chapter. As I mentioned before, in space, 3D space, we have 3 coordinates. We need at least 6 coordinates to describe one object in space. Including the translation XYZ and the rotation XYZ. It's the same. It's the same we use over here. But there are some assumptions can help us to reduce the computation because the 6 matrices for one coordinate sometimes it's a lot. It's a lot. Okay, so I think there's a powerful tool. When I say powerful tool, it means until right now, no new or novel concept can override this system. So it means, yeah, it's powerful. Okay. So this is a convention. We call convention. Convention. I don't know how to translate it in Chinese. It's called DH. It's called Denavit-Hartenberg. Denavit-Hartenberg. We can briefly call it DH form. The DH form can reduce the original 6 matrices into 4 and can help us to describe the object in space. So it's kind of a very novel design. But especially, it only designed for the multiple link robot, not for the regular system, because you need to have a multiple link. Then you have this kind of assumption. You need to meet the assumption for that. Okay, so the DH form is the main point in today's class. So hope you can clean your mind and prepare to receive the new information or new knowledge. Okay, and yeah, I think this is most of the preliminary introduction for this chapter. Okay. Hope you read through the whole chapter, yeah, because I would say it's very helpful for your English reading, okay. English reading is a kind of long-term task, yeah, like when you work out, you don't work out one day, you work out every week, at least maybe 3 times, at least, then you can keep your shape. You don't need to consider about this because you are young, but when you get older like me, you need to work out as often as you can, because if you cannot keep shape, then you can see someone, the healthy, the look will complete different. Yeah, it's not healthy, I would say. Okay. First, we introduce the kinematic chains. Okay, today I don't need to use the pen. I prepared a very good PowerPoint. Okay. So kinematic chain is something like this. I can jump you quickly to the figures. We always like the figures can help us understand more. Okay. So when you see the figures like this, you must realize it is a robot system right away. For the x0, y0, z0, later on I call it frame 0. It will be easier. The frame 0 is the base. It's the base, okay? This base is, we always define this base, call it as a global frame or global coordinates, okay? And we need to follow, I think there is some explanation, say in space, how can we describe a rotation joint or prismatic, 直线 linear, 直线型 linear joint. So for this type, you can see a cylinder is represent a rotational joint, okay? And the cylinder have a different side, right? We always understand rotation is around the side. But for the axial side, it depends on what kind of axial you define, okay? In this system, we define it as a z-axis. The z-axis always point to point out, okay? So you can have a easier imagination. That is, if a cylinder rotates by the makes sense way, okay, it means it rotates along the z-axis, okay? So the second joint we call frame 1, the frame 1. And the frame 1 will have the horizontal z-axis. As you can see, it means it rotates with a very make sense way. So we use this kind of diagram to represent the orientation for each joint. If you can realize this kind of concept, then you can receive the we call chain kinematics figures. Then you can realize what kind of robot it is. So okay, and so on. So the third joint is called frame 2, and so on. You can connect as many as you want. Okay, at this point, I would like to turn to the last page I provide over here. Then you can see more. Okay, this one is the more easier way, and it's called planar elbow manipulate. Is a planar robot. Okay, so it is okay. It did not have a very, because this is 2D shape. We have a 2D shape diagram for the rotating joint. It's okay. And for this one is a prismatic one. You have only one cylinder joint or rotation joint. The other is prismatic joint. So you can see different type. I just want to show you the different types of robot with the simple shape we represent, and this is the same. And this one is a little bit different. We call spherical wrist. Hopefully we can finish this part this week. If we can, maybe we can continue next week. But I believe we can do that. And this is the whole robot. Okay, the whole robot including maybe 2 prismatic joint and 4 rotation joint. So it's quite complicated. So eventually we will stick on this part and to do the analysis. Okay, so this is the robot we will discuss later on. Okay. Okay, so for these figures. Any questions so far? Okay. To see is to believe, huh? So before we start our derivation for the matrix, I believe we need to define some parameters. Okay, the first parameter we define over here, we always use Q instead of XYZ, because XYZ is too few to analysis, because we need more. We need a lot of Q. Okay, so sometimes equal QI, and I equal to 1 to infinity. And rotation matrix revolute, they call revolute joint is theta, represented by theta. If it is prismatic, it will denote as DI. Okay, and the more detailed description, let me find something. I always highlight for something I need to mention them. For example, we have an N joint. We always have N plus 1 links. And the joint is 1 to N, and the link is 0 to N. Yeah, we will figure out later on. I would say, although this class is a very fundamental one, but hopefully it can help you to explore further. Because right now, a lot of robot arm be mounted on a mobile platform. So in that case, you need to consider about where is your global coordinate. Okay. Yeah, your global coordinate should sit on somewhere. Okay. In that case, it is kind of complicated, because right now the mobile platform is quite popular, especially for the logistic industry. What is logistic industry? It's when you punch from APP to order something from like a PC home. They have a great, almost a full automation distribute warehouse in I believe in Taoyuan. Okay, so they can you punch how come they can deliver to you within 24 hours, because they have a lot of automation, like a mobile platform, one of them. They can grabs you whatever you order, and maybe it's a small tiny hard drive, and to the I would say it's a transportation line. Then the truck is went in beside, and then the truck will leave the warehouse maybe within 6 hours. So it's quite of I would say it's the first one, because almost 10 years ago I went to the Manchester. They have the opportunity. They asked to see how Industry 4.0 adapted in the English company, and one of them is the logistic company. Okay, there's almost a full automation. So I would say around this area, in Kaohsiung area, you still cannot see a lot, because over here is belong to like a heavy industry. The heavy industry, I would say the group, not a group, is a kind of group or cluster. Eventually, they depends on the human worker still a lot. Although they have a quite a fancy machine, they can produce with a very high speed. But if you are belong to the group for mode design in downstairs, you will understand the mode installation is kind of very difficult to apply the robot on that. Yeah, because the accuracy reason, and there are so many other reasons to prohibit the human being still can work with the very precision machine and assembly task. So I would say, but robot eventually will replace them all. So I would say it's good. Like AI, I think most of you should have some knowledge about the robotics, this kind of machine. Okay, so I will just mention that. Okay, right now we go to the mathematical part, because right now we are ready, and we are so ready to do the computation to describe the robot position. Okay, so over here, AI is the homogeneous transformation matrix. Yeah, as we mentioned in the previous chapter, they include the rotation matrix and the translation matrix. Okay, and over here, they're not called rotation matrix. It's the same, but it's called orientation matrix. Okay, and the concept is easy, as we have the homework like your system, but except that your system only have a rotation part. Okay, they have the matrix contain everything. Okay, let me show you. Until right now, they did not show any. I don't know why I put a lot of this kind of stuff here. Okay, and let's call homogeneous transformation matrix AI, and the TI is transform matrix. So to me, it's nothing different. So don't worry about that. It's just a TI equal to a lot of AI multiplied together. Okay. The fundamental one, you can see from the upper right. Every matrix contained with the rotation matrix Rn. What is the dimension for Rn? 旋转矩阵的 dimension 是多少？ Position matrix 的是多少？ Yep. So when they combine together, they need to use the redundant dimension. So the whole matrix for H, A, and T all in dimension 4 by 4. Okay. So at least you need to understand about this. So I believe that R in the bottom, the matrix R is the orientation 1. And the coordinate vector are given by something like this. Okay, it's become more lousy. Okay, let me see the easy part. So that's the math. If you cannot describe too much, just go to the formula. Will be easier. Over here, I just want to show you. I know what does it mean for the T, for the H is for the T, for the H, for the A is quite of complicated. Okay, but over here, I want to define. Over here will be easier. For one AI, it multiplies several matrices, but it represents one joint. So if you have this kind of concept, is if I have a robot, how many AI I have depends on how many degrees of freedom I have. Okay, for the 4 degree of freedom robot, I have a AI A1, A2, A3, or A4. It makes sense. Okay, but for each AI, it has multiple matrices multiplied together also. Okay, over here is an example. The example over here is we have a rotation Z. We have a rotation along with the Z axis with a theta, and the translation Z along the D1. This is called D1, right? DI, okay, DI. And the translation still Z for AI, and the rotation along the x-axis with alpha I. Oh, A and alpha is so confused, okay? So before I introduce more deeper, we are just have a concept. That is one joint. Use one AI to represent it. Joint 1 is A1. But the A1 contained with 4 matrices multiplied together. If you want to have more, if you invent the new coordinates, for one joint, there is no change at all. One joint, still A1, A2, A3. You can multiply several matrices, 6 top, together will be fine. Okay? So we have a difference. Okay? So for the AI, it's one joint. So then we go back to the previous page. What is the T stands for? So the T stands for whole robot system. Because of how many AI I have, A1, A2, A3, A4, A until 6, then I have 6, it's okay. When I multiply all A matrices together, then the whole robotic transformation matrix TI, or called T robot, is appear or show. It's okay, appear or show. Okay, so let's have this kind of relationship. So when I just describe the AI matrices stands for what, and the TI matrix stands for what, we don't have a really concept for that. Okay, but at this point, we will see. Over here, then we can look at more detail. If I represent the joint number, okay, A1, A2, A3, A4, what is the T's superscript and the lower script? It's very similar our rotation, because our rotation always refer back to the upper script, right? So in this example, if I assume my n is 6, the last one, the last end-effector is the 6th joint, 6, 2, maybe it's not 6, 1, 2, 3, 4, 5, 6, 6. Then I refer back to the 0, 1. Okay, the 0 is the original 1. So the global frame is called 0. So I refer the 6th frame to the original 1, they call 0. So at this point, you can expand a little bit more, which is my where is my, oh, here, okay. 0, 1, maybe you can do 1, 2, 2, 3, dot, 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 okay. Between frame to frame, I will call you frame, okay. This is frame. Frame number, okay. Between frame to frame, then we build up the relationship. by multiply the transformation AI matrix, AI, A1, A2, A3, something like that. Okay? Don't touch too more detail. Okay, this is more detail. But just at this point, just understand what is AI, what is TI, not TI, TN to 0, and that will be okay. That will be okay. Okay? Any questions so far? So before, in chapter 2, let me have a 1. In chapter 2, if I just want to select one AI for 1, then I have a non-rotation matrix. I have a transform matrix. Yeah, we cannot do that. Let me think. Oh, yeah. Okay, I got it. We still have this one. The and the translation and I believe in chapter 2, we start by here. We have all 4x4 matrices. Each matrix can represent rotation X, rotation Y, Z, translation X, Y, Z together. It's the same. It's the same. Okay? So if I want to describe a joint, I can list all the parameters I have. Rotation, what kind of degree of freedom you rotate with X or Y or Z? Okay. If you did not rotate, still multiply the original one. And what kind of translation you performed in X direction, Y direction, Z direction. Okay. So I just announced, last week I announced for the last, I think it's the practice exercise, the last question. There's a robot and the desk and the vision system. That is the midterm exam problem will become the problem for you. You can solve by DH form or the original form will be fine. Either way is fine. Okay, so that's why I try to describe about this. Okay, so previous one we needed 6 matrices to describe the whole degree and the position in space. Okay, but over here, okay, I just want to show you. Yes, we can have some matrix multiply together will be fine. Let's be invent. I would say invent, not discover, because invent and discover is different. Invent by the Denavit-Hartenberg, these two guys. Okay, but what is the theory? What is the concept? How come we can reduce the original 6 matrices in space to 4? Okay, they must meet some assumption. I think this assumption is a little bit too. Let me take a look. I have more, right? Okay. Okay. Over here, I just want to, because when I do the reading part, you should try the reading. Okay, reading is interesting. When you try to read and compare to the figures, then you will have a lot of marker. Okay, over here I just mark whatever we need in the table. Remember the table, the parameter table? We have A, alpha, D, and theta. Where is that? Okay, in this diagram, that is the diagram they try to explain the DH form for the assumption. But I just want to know where is the parameters in the diagram. Okay. For the first one, is easy to understand. That's the previous. I would say this is the previous, and this is the later on. So it is not necessary 0 and 1. It should become the I and the I plus 1. Okay. For the previous coordinate, the theta is the coordinate rotate along with z-axis. Precisely zi or z0. Okay. Theta is easy to understand. Okay. And the next joint we call I plus 1, or over here call 1. Okay, we skip about the alpha first. Don't care about alpha. Then these two coordinates, origin, this called origin, right? They will connect in somewhere. If they did not connect, it must to connect somewhere with the previous z-axis together. Then the shift, or call the arm. Actually, this is not arm. Okay, this is the shift called D. This is the shift. Okay, it's quite of difficult to explain, but later on we will have a robot to let you see. Okay, the true arm length is A. Okay, this is called shift. So in that case, if you have the joint 0, joint 1, 0, okay, and 2, 1, normally we will have one arm will go out, right? This is my arm. So what is the length in the diagram? Which one? This is my joint. Okay? And what is the pencil length in the diagram? A. Why? Then where is D? It is A, correct. This is D. This is still my friend 0. Yeah. If I don't have any shift, this is A. But if I have we call deviation, sometimes we need this kind of deviation because we need to install the motor. Transmission is quite large. So this is shift, I will call shift, or call, they have a special term I forgot. I just want to use the easy term to describe it. This is the shift called D. And the arm length is actually the pencil, A. Digest a little bit. Okay? So exactly it looks like this way. My D, my A, the joint. Okay? So let's go back to our figures. We are not finished yet. Okay. I want to go to the next joint. The next joint is joint 1. Okay, 0 and 1. We have a D. We have a A. The alpha is hard to imagine that. Okay. We don't care about the rotation axis at this point. We care about what is the next joint's x-axis. So over here it defined, as we know, we always define the rotation joint is Z, no matter Z0, Z1, Z2, Z3. If it is a rotation matrix, the rotation axis should be Z. Okay? But over here it defined the A. You need to go through the A-axis, and parallel the A-axis should be X. By this way, the rotation way should be over there, right? Should point to up. This is their assumption, okay? And this alpha angle is, if we turn, we tilt a little bit, okay? We tilt a little bit to somewhere. If it rotates by this way, then it can tilt to somewhere. In that case, the alpha will have an angle difference. It means if I rotate for the first frame, we rotate it in the axis way. Can we do that? Then the Z1 will alignment with this one, and the X1 will go somewhere. It's okay, because we have alpha to modify back. But for the assumption, let's say this axis must along with X1, but alpha can rotate the Z to anywhere. Okay. Digest, 消化一下, digest a little bit. Okay, you can digest a little bit later on. Why they want to do that? The bottom one is the assumption for DH. The x-axis x1 is perpendicular to the axis previous z0. Must be perpendicular. 垂直啊, okay. The second assumption is they must intersect the z0. This is so simple assumption, but this is so simple assumption reduce the original 6 matrix transformation matrix to 4. How smart it is, right? Digest a little bit. Yeah, when you first saw this, you may feel weird. Yeah. But when you saw a lot of alpha angle is different, or tilt 90 degree, always they tilt 90 degree, or negative 90 degree, then you will see, oh, okay. They can still rotate it in whatever I want. But the rotation axis must align with the z-axis, definitely. Let me show you a big picture. See? Z1 is the rotation matrix, right? Others, almost everyone is rotation matrix is the z-axis. And yeah, over here, z-axis. So what could that be? So they have alpha. They call twist angle. So along, as I mentioned, we need to align with the next axis is x. But in truth, we are not, because we have an alpha angle can adjust the x-axis. Okay, so you may feel different from that. Okay. 这有在好拍啦，在书上啊。Okay. So let's go back to this one. Put it into your mind, but later on it will be easier. It will be very easy for computation because where's my table? Because people will provide the table for you. Or if you want to design a new robot, then you need to define the DH parameter for them, or they cannot do the computation. Okay, so they provide you it's called AI, right? A, alpha, D, and theta. Eventually, in our case, in this case, class, we will provide to you. You just do the calculation. But when you design a robot, you need to provide the DH. We have a new robot be built, Central E3. We need to build up the DH for them because the DH is completely different from the existing system. Okay, and when you see, oh, okay, 0, okay, then it's aligned with our the next axis. And when you twist to 90 degrees, oh, you have a concept. They have a rotation matrix over there, something like that. Okay, got it? So let's go back to the case we have over here. Okay, so for the DH parameter, okay, next time when people ask about a question, what is the DH parameter? Then you will realize immediately, okay, this is the parameter they should provide, or we should provide. A is the link length. As the students just mentioned, this is the arm length. And this is the link offset. As the pen I show you, this is the offset length. Okay? So this two is the about the length, and this two is about the angle. And the angle, the alpha one, they call link twist, and this is a joint angle, rotation angle. So with these 4 parameters, you just retreat because this one is let me go this one. Okay, this one is rotated with z-axis, right? So you should retreat the rotation z-axis, rotate your theta. This alpha is twisted with x-axis. So you should retrieve the x-axis, rotate your alpha. Make sense? Okay. And how about the link length? I don't know link length. A. So the A is move along with x-axis. X-axis. Okay. Here. Oh. So you put the A in the x position over here. The matrix over here is x, y, z. Later one, the offset. I don't know where is the offset, or for the in the z axis. So the D is you put into the z axis spot. Then you form the whole matrix. Then you can compute the final transformation matrix for one joint only. One joint. This is for one joint. A1, A0, A26. Okay, so this is the final result. You multiply the 4 matrices together. In the future, you can use it right away. You just put whatever the DH parameter give it to you, then you can do the calculation. So we finished the preliminary introduction for the DH convention. Maybe it's not preliminary. Actually, we explain all. So we go through the whole part, then we do a little bit coding practice. Okay. So eventually, I highlight over here. Originally, we needed 6 matrices. Okay, to describe the transformation from one to B, from one to the other one. And right now, we only need what is it? 3 numbers? Oh, 6 number. Okay, 6 number. Oh, okay. This is not what I want to say. Okay, we only need a 4. Okay, then originally we need a 6. Then we need a 4. Highlight with the red fonts over there. Okay, and the reason I explained already, and hope you can understand what I'm saying. Yeah, because from this diagram, it's easy to see. Okay, so they have their concept, but they did not explain more detail. But as long as you follow the rule, okay. So in the future, we are asked to design the robot follow the rule from here, because you still need a mechanical person to match the design concept from the DH. If you did not follow the 2 assumptions, then you cannot use the easy DH convention to do the operation, to do the computation. But the worst case, I would say, is you do whatever you want, but you just go back to the original 6 matrix, multiply together. It will be fine too, but you will have some computation issue. But right now, I must say, there is no computation issue for you guys as long as you can see right now, because all the chip is so powerful, and it will become cheaper and cheaper, I would say. So, yeah, computation always is not an issue. Okay, so after you, okay, this is A, is represent for one joint, okay? And they go more detail for the assumption. For example, assumption 1 is if assumption 1 is satisfied, then we have this characteristic in our computation. So because we have the vector for the 0, then we multiply together, then they will become the final R31. When we say R31, we need to go back to the rotation matrix. We always name our rotation matrix because it's so complicated. Okay, so for the 31, it's over here. Then if we perform the inverse kinematics, then we need this kind of characteristic. Okay, so there's a reason they define these two assumptions. One of them is they want the vector from 1, 0 to the vector z00 to become R31. Okay, become R31. Then we can come out, we can compute the angle immediately, okay? And also I retrieve the original rotation matrix from 2.5, the chapter 2. And we also have this two conditions. Okay, you need to follow. Okay, so it will help us to inverse compute the angle too. So I think if we will face this kind of question, then I will let you know. But just remember something you learn in chapter 2 may be used in this chapter also. Okay, so we have two. One is for R31, the other one is the two conditions for the previous rotation matrix. Okay. And also I explain what is the mathematics for the assumption for DH2. Displacement between the O0, O1 can be expressed as a linear combination of 0, Z0, X1. Let me take a look. One little displacement. Oh, okay. Then it makes sense. Okay. So if you follow the assumption 2, if you want to compute the O1's position, then you can perform the computation with this matrix. No, the vectors. Okay. You don't need to memorize everything. Yeah. If you need, you can find from the textbook. I just retrieve some important information in the PowerPoint for the class. Okay. So there's some reason. Okay, I just mentioned on why I did not go more detail for the reason, but yes, it explained a little bit. Why we needed these two assumptions, because we can have some very special conversion for each, like origin, like the special part for the R31, then it will easy our computation. Okay. The parameter A is the distance between the Z0 and Z1. Okay, we know the arm length. How about the alpha? Yeah, you see, I explain alpha more detail. The angle alpha is the angle between the Z0 and Z1. Measure in a plane normal to x1. So you rotate with x1, okay. And the positive sense for determining is by right hand rule, okay. If the right hand rule, then is positive, okay. So later on you see the negative side, it means it rotates counterclockwise, okay. But if you rotate with a positive angle, it rotates with your, not counter, it's clockwise. But the counterclockwise is plus, okay. You need to memorize this one, okay. If you don't remember that, go back to your textbook, okay, because you just mentioned there, the positive sense. It just mentioned here, even though the same robotics, if you choose different coordinate frame, then the answer is not unique, okay, but not the answer, the frame is not unique. So different engineer will deliver different but equally correct. Okay, so you need them to provide the DH phone to you. So if you purchase a robot from like Sangyin, then they must announce their DH phone on their website, I believe. Yeah, I believe so, because we retrieve this information before. Because you need this to do your path planning and do the computation, okay? Then there's no further issue. Let me take a look. Just in case you they have a more general diagram to explain the DH. Okay, so if you are interested, you can take a look. And they are all follow the two assumptions, and they use a different explanation. So I believe I will not go to the part, even though I prepare a lot of material for that. And I even have a homework to explain. Homework explained. Yeah, you see, I have done a lot of tedious work. Yeah, tedious work. Okay. I want to stop here and explain a little bit. The convention, all we want to do is we want to know the position of any factor. As we mentioned, this is forward kinematics. We provide the angle for each joint. Then we can compute the final end-effector, location and the orientation. What is orientation? I think I explained in the class, but over here can make more sense, okay? The most difficult part for your final position is you need to provide the NSA, okay? With this NSA, it not only you have the end-effector position, that's easy because you can find out from the location. And remember what we have? T equal to AI, not AI, okay. T equal to 7 AI, but let me write it a little bit. A1, A2, AN. Then we have a matrix, say R11, R21, R31, and PX, PY, PZ, 1, 0, 0, 0, equal to NSA and 0, P and 0. Okay, that will be fine. If you understand what I'm trying to express, then you will be fine, okay? So we have a vector N, SA, and P. This is the final result we obtained from the final computation from all the joints. Then you will obtain the final orientation, for the end-effector. Okay, so for the forward kinematics, it is possible let us to try if we can reach the point and the point we can perform something. Okay, then because the NSA is so intense, so you need to compute it by this way. Okay, for the forward kinematics, then you can compute it automatically. But if there is a inverse kinematical, then you not only provide the position, PSP, YPZ, but you also need to provide the orientation. Then you will face some trouble. Okay, so later on, maybe we will face this kind of issue, but we will see. Okay, but eventually, for the forward, we can come out the information right away, NSA. So over here, it just mentioned, if you want to know the position and orientation for your end effect, just go ahead to multiply together. Then you can have the n vector, s vector, and a vector together. Also the position. So it's quite a simple. Okay.